Make this. Well, let's talk about heat capacity itself now, or specific heat.
Specific heat.
Heat capacity, specific heat, same thing. So what's heat capacity? It's the heat required to raise the temperature of an object 1 degree Celsius. So if I want to take some pure substance, water, metal, whatever, and raise it 1 degree Celsius, that would be its heat capacity. So specific heat or heat capacity, same thing. These are the same things right here. Is the energy required to raise 1 gram of a substance 1 degree Celsius. And I have a table over here.
Yeah.
So for example, air, it's 1. This is in the joules. 1 gram per joule per gram degree Celsius.
Right.
For air, aluminum 0.9, ethyl alcohol 2.45, and notice the one that we used a little bit earlier, water.
Hey, that
4.18.
That one's a lot higher than the rest of them.
But it's not that; it's just 4.
Well, that's 4 times more than the metal.
Yeah, actually, interesting thing, guys. A lot of people think that that seems like just a relatively small number, 4.18. Well, it turns out this is a huge number.
Yeah.
The highest specific heat of anything I know of is water, 4.18.
Yeah.
Most things have tiny specific heat.
And that's a good thing, because we're mostly water, and if we walked outside on a hot summer day in the sun and water had a low specific heat, we would heat up really, really fast. But as it is, our body temperature doesn't change all that much because it's really hard to change the temperature of water.
Yeah, so that's exactly right. Okay, so how could we actually figure out the heat capacity of a substance? Okay, well, the answer comes back to, it's a cool experiment. So let's do an example here to explain it. I can determine the specific heat of a metal. So if I have a metal, you can see there's a metal here in this beaker. I can then measure the change in temperature. The thing weird about energy is you can't measure it directly. I can't just stick it on a scale and say there's this much energy. I have to indirectly measure it by heating up water or some substance. Water's the typical thing that we heat up. And so basically what you can do is you can take a hot piece of metal, put it in some cold water, and you can assume that the energy lost by the metal is the energy gained by the water.
Okay.
And then you can do the calculation. Hey,
let's demonstrate.
We could actually do this very experiment here.
Right, and you're actually going to do this in class if you're in our class. It's a lab, so this will be a little demo on how to get it set up, and then you'll do it in class.
All right, so let's have Mr. Sams do it.
Okay, what we're going to show you now is how to determine the specific heat of a metal. So if you look in this beaker here, we have a piece of aluminum down there in the bottom. And it's being heated in this water, and the water is currently 92 and some change, 92.1 degrees. Okay, so I'm just going to jot that down. That's my initial temperature of my metal, 92.1 degrees Celsius.
Boiling water, 92.1?
Yeah, we don't live at sea level here. We're up a bit higher than that. Okay, so what I'm going to do is I'm going to take that hot metal and I'm going to put it into some cool water, and I'm going to see at what temperature they equilibrate at. So I'm going to use my high-tech calorimeter here. It's also known as a styrofoam coffee cup. And I have 250 milliliters of water. 250 milliliters of water is 250 grams of water. Let's jot that number down. 250 grams of water. Okay, so I'm just going to put that in here. And I also need the temperature of my water. And the temperature of my water is 19.8 degrees Celsius. So that's my initial water temperature. Now, what I'm going to do is I'm going to take my hot metal, I'm going to put it in my cold water, and the temperature of the metal will go down, and the temperature of the water will go up. And eventually they're going to reach the same temperature. So I put that in there, we'll stick our thermometer in here, give it a little stir, make sure everything's moving around. Okay, 21.1, 21.2. Okay, it's going up. All the heat from the metal is being transferred to the water. Remember, energy goes from high to low, or hot to cold, when we're talking about heat. Okay, 21.4. Maybe where it's going to stop here. 21.4 still. Still at 21.4.
I think it's 21.4.
I think we're going to call that 21.4. So that's the final temperature of both the water and the metal. 21.4 degrees Celsius. 21.4 degrees Celsius. Now, one thing I'm still missing is the mass of the metal. Now, I should have measured that before I started, but I didn't, so I figured I'd wait till I cooled it off in the water before I ran in and touched it again. So I need to dry this off, so I don't weigh the water. I just want the mass of the metal. And then I can weigh it. Make sure we're at 0. And my mass of my metal is 28.89 grams. 28.89 grams. So let's take all this data back to the computer and plug it in and calculate the specific heat of our metal and see how that matches up with the actual specific heat of the metal which we happen to have, which is aluminum.
Well, here's the data you collected, Mr. Sams, right on the screen.
Alrighty.
So what do we got? We got the metal and we got the water. So
Yeah.
we can assume that the energy lost by the metal is equal to energy gained by the water.
Right.
So we're going to use our equation, MC delta T. Actually, Q equals MC delta T equals Q equals MC delta T. But the cool thing is what Q
The
equals.
Q is the same.
The Q's are the same. So this refers to the metal, and this is the water. So the mass of the metal will be, what was it, 28.89 degrees Celsius. No, grams. Times the specific heat of the metal.
Which we're trying to find.
That's going to be just C. Times the change in temperature of the metal. Now it went from 92. Now wait a second. How did you get 92 degrees Celsius on that, Mr. Sams?
It was in the boiling water.
But I didn't measure. You didn't stick your thermometer in the metal.
No, but the metal had been in there for a few minutes,
Yeah.
so we're assuming that the temperature of the metal
So
is
we're making an
the same as the
assumption,
water.
folks. 7.7 degrees Celsius. And so that's going to be equal to the mass of the water, which is 250 grams, times the specific heat of the water. Now we do know that number.
4.18, always and
That's at
forever.
4.18 joules per gram degrees Celsius. And the change in temperature went from 21.4 to 19. I can do that in my head.
1.6.
1.6. Yeah, 1.6 degrees Celsius. Okay, so now what I'm going to do is I'm going to multiply these numbers on the left. 28.89 times 70.7. So this is going to be 2,000. I'm going to round that. 2,043 times C. And that's going to be equal to, now the other side, 250 times 4.18 times 1.6. There's no variables on that side, so that's equal to 1672. Now this C right here is not like Celsius.
No.
It's just the variable.
Right, it's like X.
It's like X. So I'm going to divide both sides by 2,043. That cost crosses the 2,043 out, so I'll take 1,672 divided by 2043 gives me
0.818.
0.8 joules per gram degree Celsius. Now I think we should check and see how
Yeah,
that
let's go
compares.
look back on the table.
We had the table a couple of screens ago, and
There it is.
Hold on, we got a aluminum was 0.90.
0.9. We got 0.8, or actually it was closer to 0.82. 0.90, that's not too bad.
Pretty good for doing it in like 3 minute experiment.
Yeah, and I think I spilled some water somewhere in there.
Yeah. So it was actually 0.82. My mistake
Yeah.
here. So the real answer was 0.90, and we had 0.80. That's or 82, right? Actually,
Yeah,
if we were to actually calculate the percentage error, how would we do that, Mr.
Yeah,
Sams?
well, we take what we got
0.82
minus what we should have
minus
got.
0.90.
All that divided by what we should have got.
0.90. So 0.08, negative 0.08, divided by 0.9
Yep.
times 100 gives what, Mr. Sams?
Times 100, it's roughly 9% error.
9% error.
And it'd be negative 9%, meaning we were
Technically.
lower than the
Yeah.
accepted value.
That's correct.
Yeah.
So, folks, that's how you do. You're actually going to do this experiment with maybe even aluminum. I don't know.
Yeah.
You'll have a metal, and you're going to try and find a specific heat. And yeah. Hey, one thing I do want to say about this that I just thought of just now is, guys, we don't have negative numbers in our temperatures. They're
Yeah.
always going to be positive. They're absolute values for you math geeks. Is that it doesn't really matter. It's a change in temperature. It's not going to be a negative or a positive number. It's just, well, it'll be positive. It'll be absolute value. So it makes your math a lot easier. Don't try and put like negative, because this actually went down 70 degrees.
Yeah.
You wouldn't say that should be a negative number. So that ends our podcast, Mr.
Okay.
Sims. Okay, we'll see you guys in class or on the internet. Bye.